It works mathematically, but remains entirely hypothetical. No one has ever detected it. A new study from an international research team suggests we may not need dark energy at all. Instead, they show that the universe's acceleration could emerge naturally from the geometry of spacetime itself, using an extended theoretical framework called Finsler gravity. If this holds up, it could change how we understand one of the biggest mysteries in cosmology. In this video, we'll break it all down. Let's get started. The accelerated expansion of the universe was first confirmed in the late 1990s through observations of distant type Ia supernovae. These measurements didn't fit a static or even slowing universe. To make the equations work, cosmologists introduced dark energy, a mysterious component with repulsive gravitational effects. But it's always been more of an adjustment than an explanation. The new study, published in the Journal of Cosmology and Astroparticle Physics by teams at Zentrum für angewandte Raumfahrttechnologie und Mikrogravitation and Transylvanian University of Brasov, offers an alternative approach. Instead of adding unknown energy, the researchers modified the geometry underlying Einstein's equations. They applied Finsler geometry, a mathematical framework that generalizes the familiar spacetime of general relativity. Unlike standard geometry, which treats spacetime uniformly, Finsler geometry allows it to depend slightly on direction or motion, introducing subtle but meaningful differences on cosmic scales. The team extended the Friedmann equations, which describe how the universe expands, using this geometry. The outcome was striking. Even in a vacuum, the equations naturally produced accelerated expansion, without needing a dark energy term. This doesn't overturn modern cosmology overnight, but it suggests that the cosmic acceleration we attribute to a mysterious force might instead reflect how spacetime behaves on large scales. The model also remains compatible with standard cosmology at lower energy levels, which is crucial. It doesn't contradict the observations that built the lambda CDM model. It reinterprets their underlying cause. This idea is important because it challenges one of the most deeply embedded assumptions in cosmology, that an unknown energy is pushing the universe apart. The lambda CDM model, lambda cold dark matter, has been incredibly successful. It matches cosmic microwave background data, galaxy clustering, gravitational lensing, and supernova observations. But it relies on dark energy, a concept introduced purely to make the math work. This new approach uses geometry itself as the mechanism, not a new energy component. Finsler geometry effectively builds acceleration into the structure of spacetime, removing the need for additional ingredients. The idea fits into a broader shift happening in theoretical physics, looking for solutions in the fabric of spacetime rather than postulating invisible substances. Other modified gravity models, like FR gravity or emergent spacetime frameworks, have explored similar ideas, but this approach is notable for its elegance. It modifies the geometric structure and lets the equations speak for themselves. Crucially, this theory doesn't conflict with existing cosmological measurements. It reproduces much of what the standard model does while offering a more fundamental explanation for why acceleration happens. That makes it scientifically compelling. This doesn't mean dark energy is wrong. It means we may have been describing a phenomenon rather than identifying a cause. If acceleration is a geometric effect, dark energy might not exist as a separate physical entity at all, just as a parameter pointing to deeper structure. It also opens new theoretical avenues: how geometry evolves, how it interacts with matter, and how these effects scale from local regions to the entire cosmos. This is not just a tweak to equations, it's a different way of seeing the universe. Any alternative to dark energy must do more than sound elegant. It must match or outperform the standard model across observational data. The lambda CDM framework dominates because it fits so well with what telescopes have revealed for decades. For the Finsler-Friedmann model to be taken seriously, it must hold up under rigorous testing. Researchers will need to confront it with key cosmological probes. Supernovae. These were the original signal for cosmic acceleration and remain a benchmark for testing expansion histories. Cosmic microwave background, CMB. Tiny fluctuations in the CMB encode the geometry of the early universe with exquisite precision. Baryon acoustic oscillations, BAO. These serve as cosmic rulers, sensitive to how expansion evolved over time. Gravitational lensing and structure growth. These reveal how matter clumps together, offering another way to probe the underlying dynamics. The model already aligns with some aspects of this data, but full compatibility is far from guaranteed. Testing will reveal whether the geometric explanation is robust or if it introduces new tensions. On the theoretical side, researchers need to study how perturbations behave in a Finslerian spacetime. Can this model explain not just cosmic expansion, but also structure formation. The emergence of galaxies, major shift, not a discovery of a new thing, but a reframing of the laws that describe the cosmos. It also opens an intriguing door for fundamental physics. If space-time geometry drives cosmic acceleration, it might connect with quantum gravity research, linking the largest structures in the universe with its smallest scales. But this is still early work. Dark energy remains the standard explanation because it fits so well with what we currently see. Whether geometry can fully replace it is a question only data can answer. A new study suggests cosmic acceleration may come from space-time geometry itself. If proven, this could redefine our understanding of the universe. The next step is to test it against real data.